I'd like to spend a few minutes talking about this concept of experimental uncertainty, especially as we lead into Lab 1 and folks are working on the pre-lab. I know that some of you may have some questions stemming from this experimental uncertainty analysis that might not have been satisfactorily addressed during the pre-lab lectures. So I'd like to get everyone on the same page here in terms of what we're doing and what equations apply. So we're going to go ahead and assume that we've collected some data set X, right? We have a measurement variable X. In the pre-lab, you've been given two measurement variables, X1, X2. So from your measurement variable, you're going to be able to compute, or from your set of measurements of however many variables you have, you're going to be able to compute some sample statistics. In particular, X bar, which is the sample mean, and S sub X, which is the sample standard deviation. And I like to assign some sort of plain English interpretations to these, where X bar can be thought of as our best guess or estimate at the true value of X. And S sub X is indicative of the amount of scatter around X bar. Okay. Now we also mentioned in the pre-lab lectures these ideas of types of uncertainty limits, or as we call them, a bias limit and precision limit. So the first of these, B sub X, is what we call a bias limit. And this has a lay interpretation as the maximum estimated error in X bar. That is, if this quantity right here, the sample mean, right, if this is our best estimate of X from collecting a bunch of different measurements, how far could that be from the truth? And that is something that's impossible for us to know exactly, right? Because if our best estimate is still off, how do we know by how much? So there's this idea of estimating, right, of projecting something that we do know about our measurement to figure out how far we think our measurement could be off from the truth. And we'll talk a little bit about that. Second one is P sub X, which we call our precision error. And this can be thought of as the bounding values of the random error containing some percentage of our measurements. That is, if we have measurement of X, let's say there's some X truth. This is the value that we seek, right? We're looking to get this blue dot here through our measurements. However, because we are using flawed equipment, or because the temperature changes during the day, or for some reason we obtain X bar, and there's some scatter around those. So the distance from X bar to X truth, right, we would estimate this as Bx, and the amount of error caused by random fluctuations in our measurement we would call px. So how do we get these values, right? I mentioned that with bx in particular, it's impossible to know exactly how much error is present if you don't have access to the true value. Typically, it's a tricky one to do well, but typically you have to resort to estimation or looking it up. So when you're estimating the bias limit, rules of thumb will apply. Like if you're using a ruler, you'll take the smallest increment of measurement on that ruler and cut it in half and say, my bias limit is plus minus 1/2 of the smallest unit of measurement on this instrument. If you're using a digital instrument like a stopwatch, you'll say plus minus the smallest significant digit on that digital output. So it's a way of saying, I cannot resolve my measurement finer than this. So it could be off by up to, the bias limit amount. The precision error is much easier to estimate because it has to do with the random fluctuation from measurement to measurement. It can be tied back to this sample standard deviation, right? When you repeat measurements of x, let's say you take 10 measurements of x, they're going to be scattered around an average, and so you'll get some value for the sample standard deviation. Now, the precision error, it says here, we've defined it as the bounding values of random error that contain some percentage of measurements around x bar, around your mean, your sample mean. So this can be thought of as a type of confidence interval. And so we compute, we define px as being equal to t times sx, where sx is our sample standard deviation here. And t, we're going to define as what we call a coverage factor. Now, it's very common in industry and to use a value of 95% here for this, for the percentage of values to be contained by your precision error limits. This is supposed to be precision limit. And so in this class, we're going to go ahead and use this 95% confidence interval idea. That is to say that if we have, if we have our average measurements and we have, plus minus p sub x, we expect that when we go in to take a measurement, right, if we take 100 measurements, ,95% of those are going to be contained within this plus minus p sub x. And so the way we do that is by assigning a value of t equals 2 for our 95% confidence interval. So this should look familiar from the pre-lab. Px equals 2 times Sx. Okay, so at this point, we haven't really covered anything new. In the pre-lab, you've been given your bias limits in the problem statement, and you've been given this formula right here. So what you're expected to do is actually calculate the sample mean and sample standard deviation for your measurement x1 and for your measurement x2. And from those, you can compute the precision limit. You're given the bias limit, and those two things are combined for our total uncertainty, which is defined as u sub x squared is equal to b sub x squared plus p sub x squared. I like to think of this as if we have our bias limits and our precision limits, right, plotted as independent axes in 2D space, right, we might have some values that we figured out, right, where this is over, it's b sub x by p sub x in our coordinate space, then the total uncertainty would be defined as the length of the vector from the origin to that point. Length is u sub x. So this should enable you to answer part A of the question, or of the uncertainty question in the pre-lab, by computing the precision limit and total uncertainty on x1 and on x2 by following this procedure. The next question is, what does this do to the so-called data reduction equation, right? We're given measurements, which in this case are x1 and x2, but let's go ahead and say maybe we have x3, x4, so on and so forth. There can be as many measurements as you care to use, which are fed into some data reduction equation, which spits out some result of interest that we're going to call R. Okay. Typically, when you're doing an experiment, R is the thing you're interested in. In lab 1, we seek, for example, the kinematic viscosity of a fluid, the measurements of the things we actually have access to, things like length, time, distance. So the way we bridge our measurements to the thing we actually want to know is through this data reduction equation. And so this will usually take the form of R as a function of x1, x2, x3, x4, etc. So let's so just as with the measurements, right, we have bias and precision limits, we also have bias and precision limits on R. So we're going to have a b sub r and a p sub r. Let's first look at this bias limit on R, right? So just as with the measurement, b sub r is our bias limit, and again, just as with the measurement, this is indicative of our estimated max error in our best guess at R, okay, in R bar. How do we find this? The same problem applies here, right? We don't know what we don't know. We know the average value of R, right? If we're given 10 values of x1, 10 values of x2, and an equation that turns x1, x2 into R, we can compute 10 values of R. We can go ahead and find, I should mention this, we can go ahead and find R bar, right, and S sub R. That is, again, the sample mean of R and the sample standard deviation in R. However, we don't know what the true value in R is. So how do we make that estimate of the bias limit? And this is what we call propagation of uncertainty, right, or propagation of bias error. So the formula that you're going to want is what we call propagation of bias error specific to uncorrelated errors. And this says that b sub r squared is equal to the sum I equals 1 to n of theta I times b sub I squared. So we have another square them up, add them up sort of situation. The question is, what are we squaring and adding? What is this theta I that's inside this argument here? So theta I is defined as, oops, I wanted that in black. Okay, theta I is defined as the partial derivative of r with respect to x sub I, evaluated at x1 bar, x2 bar, x3 bar, etc. In other words, to find theta 1, this is called the sensitivity coefficient. Right? So for example, go ahead and box that in, that's important. So for example, to find theta 1, you would take the derivative of r with respect to x1. Okay, that's going to give you another function. It might contain some x's, whether they're x1s, x2s, x3s, what have you. Then you're going to take your mean values of x1, x2, x3, right, your sample means, and you're going to plug those into whatever you have, whatever that equation is, and what falls out is just going to be a number, right? It's no longer going to be a function. You'll get a constant. And that is, in essence, the slope of r with respect to, in this case, x1. It is how sensitive r is to changes in x1. And thus, if there is some amount, some bias error in x1, that is how much it might incrementally contribute towards a bias error in r. Okay, this is an extension of this idea of a Taylor series expansion, but I'll spare you all the messy graphs for that right now. So let's go ahead and run through a very simple example calculation here. Let's say you're given x1 and x2. Okay, I'm not going to list any numbers here, but let's say that you're able to calculate that x1 bar is equal to 2, and x1 or x2 bar is equal to 3. Let's say you're given that b1 is equal to 1 and b2 is equal to 0.5. Okay, let's say you're also given a data reduction equation that says r is equal to x1 squared plus x2 squared. So partial r by partial x1 is going to give you 2x1. Partial r by partial x2 is going to give you 2x2. All right? So to compute theta 1, this is going to be 2x1 evaluated at x1 equals x1 bar. Theta 2 is equal to 2x2 evaluated at x2 equals x2 bar. So we have x1 bar and x2 bar right here. So let's take these values and plug them in right here, which gives us that theta 1 is equal to 2 times 2, 4, and theta 2 is equal to 2 times 3, 6. Okay, so we have our sensitivity coefficients wrapped up right here and here. Now to figure out the propagated bias limit on R, we're going to apply this equation right up here. So B sub R squared is equal to, again, the sum from I goes 1 to n of theta I bi squared, which in this case, because n is only 2, right, we only have two variables going into R, this gives us 4 times, right, there's theta 1, 4, b1 is equal to 1 squared plus 6 times 0.5. So we have 6 times 0.5 squared, right? And this gives us 4 squared plus 3 squared. So that's going to be 16. It's going to be 9, right? Equal to 25. So b sub r is equal to the square root of 25, which gives us 5. Okay, and there we've calculated the propagated bias limit on r from the bias limits on x1 and x2. So when you're taking measurements, it's usually much easier to make an estimate of the potential error in a specific measurement than it is to make an estimate of the potential error in some complicated result that you're computing using equations. Okay, so you can go ahead and apply this method for calculating the bias limit to the next question on the pre-lab. So let's go ahead and head back up here, right? We've covered how to get the bias limit on R. What about the precision limit? Well, there are two approaches to getting a precision limit on R. And in this case, right, for this pre-lab, we only need one of them. And this is known as the method for repeated measurements. Precision limit for repeated measurements. The idea here is, right, you're able to calculate R as many times as you have measurements of x1 and x2. In the case of the pre-lab, you'll have 10 values of R to work with. So since P is intended to represent the amount of scatter present in whatever variable it's ascribed to, it's easiest to just calculate that directly for your output. So P sub R is going to be equal to T, right, times S sub R. It's precisely the same formula that we used in the measurement variables x1 and x2. However, there's a twist here. I believe that in the pre-lab you're asked to find not P sub R, but P sub R bar. Okay, this is known as the precision limit on the mean value of R. I should mention here, I left it unsaid that in this class, right, this is going to correspond to T is going to be equal to 2, so this is 2 times S sub R. So P sub R bar is equal to T times S sub R bar, which where S sub R bar is known as the standard deviation of the mean. All right, the idea here is that if you were to calculate a bunch of individual values of R, right, there's going to be some scatter to them, which can be described by the sample standard deviation on R. If you were to go and do this experiment repeatedly, and each time you did the experiment you calculated 10 values of R and you averaged them together, then what you're essentially doing is looking for scatter in the value of R bar, right, that mean value of R in this experiment, and then how that varies from repetitions of the experiment. So rather than the deviation, the amount of scatter in just R, you're looking for the scatter in the average values of R from experiment to experiment, which is generally going to be much smaller. Okay, because averaging is such a good way of sort of smoothing out random error in the data, you're able to tighten up your estimate of something by taking the average and comparing those averages. So P sub R bar, or I should say the sample standard deviation of the mean, S sub R bar, is equal to S sub R over the square root of M, where M is the number of data points that you're working with, right? The number of repetitions of that experiment. So in the pre-lab, M equals 10. So if I haven't confused you yet, the idea here is you find your sample standard deviation on R, right, by computing R for each value of x1 and x2 and looking for the standard deviation. And then you divide that by the square root of the number of values that make up that standard deviation estimate. Then you go ahead and multiply that by 2. Oops. 2 times s sub r over the square root of m. And that's going to give you your precision limit on R bar. Finally, how do you combine, right, your bias limit on, so there we go. We've covered how to get your bias limit on R and how to get your precision limit on R. The last question is, how do you combine, or I should say on R bar, how do you combine these to get the uncertainty on R bar? Well, it turns out, right, you might be thinking, well, I have an R bar quantity here and I have an R quantity. Well, it turns out that because your bias limit here, right, is an estimate of how far your average could be from the truth, that it also describes how far your, I should say that the bias limit on R is equal to the bias limit on R bar, right? So the equation that you need to worry about is R, the uncertainty on R squared is equal to P sub R squared plus P R squared. So you have this from the propagation of uncertainty. You have this from looking at the scatter and your values of R, and that allows you to get the total uncertainty on R bar. So that wraps up the overview of the necessary equations for the pre-lab uncertainty analysis. If you have further questions, shoot me an email as soon as you can, and I'll try to clear things up. I'll make sure to have time, office hour time, where you can come in for help on pre-lab questions.